All right, and we're back. Um, I will be continuing on solving first-order ordinary differential equations. This time, instead of using the analytic solution and plotting it, we'll be using our own numerical integrator developed through Python and use that to solve our first-order ordinary differential equation. So you might say, you might have noticed that what we actually have is, of course, that there is no acceleration in the x direction once this thing is thrown, and in the y direction we have an acceleration that is equal to negative g. Of course, if we then integrate that to give us our velocity and then integrate that again, we get our position, but that's a second order differential equation, and I wanted to just start off with first order differential equations. Second order differential equations are basically just doing that, solving two first order differential equations, but I'm just going to start with first order differential equations. So I'll start with velocity and then from there solve the position. Or in some instances I will start with acceleration and solve for velocity, and then we'll deal with position later on in the week or maybe next week. All right, so now that we have our analytic solution, we're going to discuss the numerical solver. So how do we get these computers to actually solve these differential equations on their own? Well, these derivatives, or these first order ordinary differential equations, are actually just saying that we have the first order derivative in x is equal to this velocity, where this dx by dt is the limit of delta going to 0. So in a limit where we actually have these numerical solutions, instead of having dx by dt, because it doesn't actually go to infinitely small dt, we have delta x by delta t, where delta t is some finite time step that we can actually have in, that we can actually use in our computer algorithm. But you can actually just directly solve for this, as you have delta x then will be v of t times delta t, as we have here. So delta x is vx of t times delta t. But of course, because we've integrated by doing this, we're saying that there has to be some kind of constant. There could be some original position, and same thing with delta y. But v of y is going to be this v naught yt minus gt times delta t for each little time step of delta t. So what we have to do then is put this into a little loop. And so our x of n plus 1 will be, which is the position, the x position of the next time step will be the x position of our current time step plus the velocity at this time step times this delta t times this time step. And so for this case of a ball being, the parabolic motion of a ball being thrown on the surface of the Earth, we don't have any change in the x velocity, so our x of n is just going to be, or our x of n plus 1 is just going to be the x at the current time step of n plus this initial velocity x times this time step delta t. And that'll give us our next position step. Our y of n plus 1, so our next y position will be the current y position plus this vy times delta t. And so that is our y of n, this current position, this current height, plus this current velocity in y times delta t, minus the gravity, this acceleration due to gravity times t times delta t, as is shown there. Okay, so this is how we, I guess, kind of write like a pseudocode. So this is the differential equation that we have to start for x, and we similarly have one for y, so we can get this delta x equal to v delta t, and delta y is equal to vy delta t, and then we put this into what this algorithm would be, is our next position step is our current position step plus this velocity times this delta t. So keep in mind this is the Euler integral. So this is called Euler integration, and that will be shown in the next slide. And this is what does this look like in Python? So what we have is this delta t. So these time steps delta t we will call in Python this capital DT. And t is just our linspace. So we've previously written, we would have t here is equal to, t is equal to np.linspace 0 to, I don't know, what was the time that I had there, to 5. And then we have, say, some number of steps, something like that. So that would be our t, and then dt will be this first or the second value in this array of t minus the first value in this array of t. And then we set, and so that gives us our delta t. You could actually choose anywhere that you want because this is linearly spaced. It doesn't matter where you choose this, just make sure that they're one next to each other. X naught, we say that our x naught is equal to 0. It's easy enough to choose wherever we want. We set our x naught equal to 0 and our y naught equal to 0. So xte will be some pre-counted, we've cleared memory for an array called xte, and this will be our x of t. And then we put this into a for loop. And so how Python handles for loops is we say for count t. I like doing it like this, so we just have to have some counter. And then I like calling it what we're counting over. So if we're counting in time, then we do count t. If we're counting in space, I'd call it count x, something like that. So for count t in range from 0 to n minus 1, so it starts off from the first value. And so as you notice here, the first value in our array is 0, so the first value in this count will be 0. And then we want to have nt steps. So I guess we would have here, I guess we'd call this nt, and we would have something beforehand that says nt equals 10,001, some value. And then we have and it ends with a semicolon, or full colon. Note that for loops are indented. There's no end statement in Python. It just does an indentation. So be careful when you are writing these out that you notice the indentation, because if you have this for loop and some parts are brought back without indentation, then that exits the for loop. So be careful you have the right parts indented. That's kind of the trickiest part with Python. So we have this xte, so this value in this array of count t plus 1. So since we're starting at t equals 0, we want the next value. So the second value in this array will be v naught x times dt plus x naught. And then, so x naught we started at was 0, and then we end this loop with saying that x naught is this current value of xte. And then we just put that into this for loop, so that means that this initial value here will be this initial value here, and then xte will increase by an amount v naught x times dt. So this is Euler integration, but it happens to be that because our v naught x is actually not a function of time, this ends up giving us exactly the answer. So you can see that here, that our x-coordinate here is perfectly increasing linearly with time, and that is just saying that Euler integration actually works for something that is just linearly progressing. However, we have y of t. We also have to create this array, so np.zeros. So we call this numpy package, and zeros just clears an array of the size of nt. So as we've already defined nt up here. And then again, we just say that the initial height is equal to 0, so y naught equals 0. And then we have for count t in range 0 to nt minus 1, and this full colon. We can use count t here and count t here. If you want to, you can call this count tx and here count ty if you want to make sure that these two arrays are separate. But it doesn't matter because once we enter this for loop, it resets this counter. So yte equals count t plus 1. So we do the exact same thing as we did for x, equals v naught y times dt minus g of t count t. So now we're calling this t in this array. So how long this has been progressing in time. will be as part of this function times dt plus y naught. So this is exactly like what we have here, that y of n plus 1 is equal to yn plus v naught y delta t minus gt delta t. So g of t, and so we want this specific time. So gt at this count t times delta t plus y0. And then again, we change this y0 on each iteration. So this is an example. I don't know exactly how many steps there are, maybe 100 steps or something like that. And the analytic solution is, of course, the exact solution because we can solve that exactly because it's quite simple. But if we put in Euler integration, we can see that there's a little bit of a difference between the two. So let's look at this code. So we're right now at this time for this point for Euler integration. And so as we've said, we've already defined our t. So we have nt is, I guess we only have them as 10 points. And we go from t from 0 to 5 nt, just like we had before. So this is to count the clock here, this ti. So we call it like ticker and talker. And so we have this initial timing is time.time. And then we have our time step, dt is t1 minus t0, as we had before. So you can see that all this is the same as we had wrote before, and then we can plot this. So we plot this. If we only have 10 steps, you can see that this is the analytic solution, and this red is the approximate or our numerical solution, and you can see that this is quite off. So if we increase our number of steps, where's nt? Oh, there we go. So let's increase it to 100. So now we're at 100 steps, and we go here. This now shows us that this is closer. So this is with 10 steps, this first one, and then with 100 steps, you can see that this is closer. And oh, it's still showing down. And so now we can increase this. Here, I won't bring this up again. So let's see. Oh, here we go. So now I'll just be calling this part. So now we'll go to 1,000 steps. And we'll run this again. And you can see, oops, sorry, I ran the wrong one. Here we go. That's what I want to do. All right, now you can see with 1,000 steps that our numerical solution agrees quite well with our analytic solution. So that means that for Euler integration, which I said is not a very good integration technique, but it is exactly what we're trying to do, but it requires a very, very small delta t. So so Euler integration is kind of like a good way to almost like back of the envelope check your answer. If you don't really care about computation time, if it's something simple like this, you can run it because you can kind of get the answer. If you want to just check to make sure that your answer is converging to something that seems reasonable, then you can just increase your number of steps by an order of magnitude at the cost that it'll take an order of magnitude longer time. So if something takes a fraction of a second, making it run an order of magnitude longer isn't going to really take up too much of your time. But if something's taking 10 seconds and you want to check to make sure that this is okay, and so you increase your number of steps or you decrease your time step, then obviously that's going to be taking 1.5 minutes, and that's starting to become kind of not so fun to wait around for, especially if you're trying to debug your code. So that will be it for the Euler integration, and the next tutorial we'll be talking about midpoint integration.